So I've backed up a little bit from where we left off last time, just because I want to make sure that you understand this rather than breaking it up. Thermography, just a quick review, is an indirect process. That means the energy we're using is actually absorbed by the part. Its form is changed. So infrared radiation, when it hits a part, okay, infrared radiation traveling through the air, you don't feel infrared radiation until it actually hits something. And then that item, that object's temperature increases, right? So when the sun is on your skin, you know, it can be a very cold day outside, but you'll feel your skin warm up, right? And so it's the same thing happening with objects. And so that energy is absorbed, or if, you know, there's less infrared radiation in the atmosphere than what the part would give off because of its heat content, it could be, you know, it could lose it as well. But then once that energy hits the surface, a portion of it is absorbed and then it diffuses through the material. So, you know, even though infrared radiation, you know, you think of a block of metal, is only touching one side of it, eventually the back is going to become warm, right? That heat energy is going to work its way through. And so then what you actually feel, or what you actually sense if you touch that, or if you're near hot metal and you can feel it coming back to you, that is that radiation re-emanating from the pieces, turning back into infrared energy and then traveling through the atmosphere, the air, and hitting you. When I say atmosphere, it doesn't have to travel through the atmosphere, right? Infrared radiation travels through the vacuum of space before it gets here. So it's you know, I say through the atmosphere, but it doesn't have to be an atmosphere. You don't have to have a medium to convey infrared radiation. Whereas heat, you actually do have to have a medium to convey heat, to diffuse the heat energy through it, right? Space is very cold, but there's a lot of infrared energy coming from the sun that makes it here, you know, where we're at. This is versus those direct processes where radiography, for instance, or ultrasound, you know, where you're injecting, say, ultrasound, you're putting a sound wave in, you're looking for that same sound wave to come back to you. So I want to show this one more time just because there's an important point here. So here is that infrared energy coming in. It's going to contact our test object, and a small amount of it, or a certain amount of it, depending on the reflectivity of the surface, is going to be reflected. And it's going to change it a little bit. It's going to go from a shorter wave to a longer wave, but you know, we don't want to measure that. That's just bouncing off. What a certain amount is going to be absorbed if the material is infrared conductive, or sorry, infrared transparent in any way. A certain amount of energy can pass through. There's only certain materials are that. So like the cameras we have, the lens, for instance, allows infrared energy to transmit through to the sensor that's actually picking up the, you know, the heat. But then a certain amount is absorbed, and then that absorbed energy becomes heat in the object. And then that heat, when it gets back to the surface, is going to leave the object as emitted infrared energy. And you can see here, this is what I was talking about with, you know, heat will hit one side, you'll feel the heat, eventually it'll work its way through the object, and you'll be able to feel it even on the backside. So when we're using the thermal cameras, we can look at the same side of the object that we're applying our heat source or our cold source, or we can look at how that energy transfers through an object. We can put heat on the back side, for instance, and see how it transmits, you know, how it diffuses and then ultimately comes through to the opposite side. Not transmits, but diffuses and then emanates from. So again, this is what we're looking for, is that heat that's emanating, retransmitting. Okay? Compared to those sound waves that are bouncing, you know, it's that sound wave going in, bouncing, and going back to our transducer for something like ultrasonic, which is a direct process. So the surface temperature is going to be based on, you know, that heat hitting it, but then how it moves is going to be based on the geometry and the contrasting thermal properties of the material. So geometry is affects what we're able to see. And the biggest thing here is the limit, what we call a limit for detectability. And so we can have, if we have damage to an object, for instance, that damage can be, you can think of something like a crack. So if I have an object that has a crack in it, so here's my block of material, and at this end we've got a crack in it. At the surface, say we're imaging it from this top surface, the area that we can see is very, very tiny. It's just the width of that crack, right? And those may be so small we can't see them with the naked eye, okay? But it has a very long depth. So, here is our, we'll call this the diameter, is this amount of surface area right here compared to the depth right here, right? So something like this, if you use that equation, if we take the discontinuity diameter and divide it by the depth, what do we get? If we have a diameter that's very small over a depth that's relatively much larger, what do we get? Do we get a big number or a small number? We get a very small number. It's a fraction. You'll say the diameter we say is 1 and the depth is 20, 1/20th, right? 0.05. Right? That's much smaller than 1, right? So this is not something we would be able to find very easily with thermography. So anything where that discontinuity diameter divided by the depth is less than 1 makes it very difficult to see. But say you have, say this was a composite, and you have an area of delamination that looks something like that. And if you were looking at this from the top, it'd be, some kind of a circular or some kind of a shape, right? We can say now, the diameter is here, and our depth is just, is just this little tiny distance right here, right? So now, say we have a diameter of 20 and a depth of 1, that's going to be much greater than 1, right? So that's going to be something that we're able to detect. So what we're looking for, now it can be subsurface. You can see this doesn't actually break the surface. It doesn't need to be surface breaking. But what that's going to do is it's going to affect how heat transmits, or how heat travels through this material, right? If we were to put heat on the bottom of this example, the heat purple, if we apply heat down here, that's not a great marker, that heat is going to work its way up through the part. Here, it's going to be able to get to the top surface fairly easily. Over here on the right, it's going to be able to get to the top surface. But right here, it's going to, if that's a little bit of an air pocket, for instance, a delamination, there's a little bit of air in there. Air is a very good insulator as long as it can't convect or move around. That's going to prevent that from traveling to that top surface. Or if we've heated this part and now we put it into a cool atmosphere, the latent heat in here is going to leave the part faster in these areas than it is in this area, in the flawed area. And so we can see that difference by looking at differences in surface temperature using a thermal camera. The other thing that's going to happen is contrasting properties, and that's occurring, those contrasting properties is occurring because of that, where I was talking about, like if we have a delamination here, there's air, the material, the solid material is a better conductor of heat than the air pocket. And so you have a contrast in the thermal properties of the material. You have a diffusivity contrast. The heat's diffuses differently through the air pocket than it does through the solid material. So that's what we're picking up, is that we have to have, again, here, this will be, there is a little bit of, we'll call it an air pocket in the crack, right? There's a little separation, there's air in there. Now, heat may not transfer left to right here, but if we're imaging from the top, we won't be able to see that pinpoint very well for the surface breaking crack. Okay. So we have to know, what kind of flaws are we looking for? If we're looking for flaws that are more this way, one option is to say, okay, we need to use a different test method. The other option might be maybe we need to image it from this end rather than from the top. Right? We have to think about what our expected flaw is so that we can make sure that our diameter divided by our depth is greater than 1. Okay? Or maybe you need to use, ultrasonic from one end to the other if it's a composite part. Something like that if thermography is not going to be possible. Okay. So ultimately, thermography is good for a wide area damage, wide area discontinuity detection. It's not good for small or deep damage. But because this wide area can be below the surface, we can find subsurface flaws that we may not be able to find with some other techniques. Visual inspection, for instance. So when we're doing this, though, earlier I talked about whether we're doing qualitative or quantitative inspection, right? Qualitative is there damage? Is there a discontinuity? Quantitative is how big? Okay. If we need to get into that measurement area, we have to be careful because the apparent size, the way this will show up, doesn't always match the actual size of the damage, right? This crack I drew that's below the surface, you're still going to get some heat transfer, maybe from this outside past the edge of it, which might make it look smaller, right? The heat energy over here is going to work its way left or right. It doesn't just go up and down. It's going to go every direction in the material. Or, if you have moisture in there, that moisture is going to be pulling extra heat away from the areas to the sides that may make it appear larger, for instance. So, the apparent size and the true size are not necessarily the same. When you're directly viewing something, indications typically appear larger than they are, okay, when you just look at them. Part of it can be how long it's been. So what I mean by that is as you're heating or cooling a part, we often will take pictures, take thermal images at multiple time points after or during that heating or cooling process. It's not just one picture at a certain time or image. You might, so one of the tasks you're going to do is take a composite panel, you'll put it into an oven to get it warm, and then you'll pull it out and you'll see how the heat leaves that object. Well, it's going to look different. When you first pull it out, if you take an image of it right away, the whole thing looks the same. Everything's the same temperature if it's been in there long enough to fully heat soak. But then maybe a minute later, you'll start to see areas where repairs have been done versus those that haven't. 2 minutes later, you might start to be able to see a honeycomb structure inside of it because the heat's going to be leaving different areas at different rates. So you often have to take images over time, and over time you may see different things that become visible. If we actually need to get into hardcore measurement, you start to get into things like pixel processing, and now using machine learning and AI and other algorithms to look at, where it's looking pixel by pixel. What's the temperature here compared to here, compared to here, compared to here, and what does that mean? Right. And so that's what we get into processing. That can get rid of, or it can kind of compensate for some of that diffusivity difference that you're getting. Okay. Other things, accuracy is reduced as the lateral dimension approaches the detection limit. So what that means, simply, accuracy is better for larger indications. As we go from this wide, shallow indication to this narrow, deep indication, as we move from something one to the other, our accuracy is going to go down. If you have a much larger, wider, shallower flaw, it's easier to get a more accurate size on it than if you have a narrow, pinpoint flaw. And early process acquisition of data is less affected by the diffusion of energy. Okay, you often can get a more clear picture of size earlier on, but the problem is too early, you don't have that contrast. That's what I was talking about. We take the panel out of the oven that's got a repair area and non-repaired. Well, when we first pull it out, everything's pretty much the same temperature. You can't see that difference. It's only after time where that difference starts to become visible. But if you leave it too long, it gets fuzzy. it's hard to see the contrast as well. It's not as sharp. So it's a balance. That's why we would take images over time to try to figure out where can we best, where can we best see what we're trying to see. Is it 30 seconds after we pull it out? Is it a minute? Is it 2 minutes? Is it 3 minutes? Okay, that's in our oven case. Some thermography uses what's called flash. It takes a light, basically does a brief fraction of a second flash pulse, and which is a very tiny amount of energy. It changes the temperature just slightly. But your camera, if you have a high-speed thermal camera, it may take several pictures in a second after that flash to see how it looks. I'll show you what some of those look like here in a minute. So above is direct viewing. This bottom one, which is a composite panel, this has had some pixel processing done on it for how well is the epoxy in the panel. But here above, this direct view, who can tell what that is? Any idea? What are we looking at right there? Anything look familiar in that picture? Shape-wise? I'm talking just shapes right now. You don't need to analyze what it is necessarily. Any idea what that top picture might be? It's like a flight control. Elevator. Okay. Close. It's a flap. So that's that whole flap panel that's drooped down. Here's the canoe fairing that the flap drive is inside of. What do you think is going on here? That's water. That's what water ingress looks like. That's what I was talking about, where one of the most common uses for this technique in aviation is to look for that right there. Okay? More than likely, this plane was flying. It was up at altitude. The water in there got cold or even froze. Planes come down and landed. Now, it's not super warm. Now, this is in degrees Celsius, but you can see the warmest spot on this airplane. So you got to take into mind, red, everyone sees thermal images. They see red means hot, right? Well, in this case, red to white means 10.9 degrees Celsius. $30 degrees Fahrenheit? Do you know where are we at with it? Yeah, 30 to 40 degrees Fahrenheit, something like that. It's pretty chilly still, right? It's not, room temperature is 21 degrees Celsius or so. So like halfway between room temperature and freezing. And then you can see the coldest part is 0.1. That's the freezing temperature. So that tells me that was probably ice or very close to ice while it was in flight. Okay. So, I talked about the basic process. Now we'll get into the details of some of them. So the first thing we have to do is excitation. And so we can do different types of passive heating, or we can do active. So passive heating is typically used for qualitative. Is it there? Is it not there? Is there moisture in the flap? Is there not moisture in the flap? If we need to figure out area of it, it might be a little harder to kind of measure that. But typically the way we do this, aviation especially, is solar or ambient. Solar being planes sitting in the sun or planes not sitting in the sun. The other one is ambient, would be planes in the hangar. Hangar's warm, it's cold outside, we open the door and the plane starts to cool down. Or if you have a hangar that's relatively cool and it's hot outside, open the door, plane starts to warm up. That's ambient passive heating. So minimal equipment, you just need a camera. You don't need any kind of heating or cooling equipment. It's very uncontrolled, right? We're kind of at the mercy of the weather. We're at the mercy of where the plane's located. We're at the mercy, is the plane sitting in the sun? Is it in the shade? Do we have to move it? Maybe you need a tug in that case. But the temperature changes in the aircraft, they're observed using a thermal camera after any of these situations. So, landing as it warms up, moved indoors, out of the sun, moved outdoors into the sun. Anything like that can induce a temperature change in the aircraft without actively doing something, without actively trying to heat or cool it. If we go into the active realm, you've got a whole bunch of options that come available to you, kind of shown here. And I'll look at what these are. but things like convection, cooling, blankets, lights. So active heating, more qualitative. You can do quantitative. We're going to do qualitative using active heating. That's what putting the panel in the oven is. And I'm not. You can approximate sizes. You can give me some quantitative measurements, but majority is looking at what can you see. Can you see the repaired area? Can you see the honeycomb structure underneath the surface? You know, can you see elements of the construction? And we're going to do that by active heating, but you know, these are some of the uses for active heating, and that what you see there is an infrared lamp. We had lots of these sitting around the hangar. Any idea what they were used for? What's that? Anyone work in airframe at Duncan? And have you used these heat lamps? You've never used heat lamps? Curing sealants for the most part. They use heat guns? Okay. We would do big areas and have to just put a heat lamp at the plane and try to get it to cure. We also had to cure a plane in like now because it had to fly the next morning, where Duncan has the luxury of time that we didn't have. But we had in fact, we had quite a few heat lamps sitting around the hangar, mainly for sealant curing, but we could use them if we needed a heat source for something like this. So, you know, this is where you start getting into, again, those actual measurements, quantitative measurements, thickness, depth, area, size, thermal diffusivity, if you want to see, you know, materials, things like adhesion, delamination. That could be post-repair inspection. You did your composite repair. Did you do your composite repair well? You know, are there any air pockets between your patch and the skin? You don't want that to be the case. You want to have full bonding, right? So other things we can do are optical. So this is an optical heat lamp. This is one where you just put it on and it gives off infrared energy. Other optical heating methods, visible light or visible with infrared. You know, this bulb right here is giving off some visible light. The visible light's not doing much. It's also giving off quite a bit of infrared energy. Okay. So visible light and the infrared portion of it, that's right on the edge of the spectrum, used to heat the surface. Advantages, it's non-contact. It can be focused in a small area, or you can heat a rather large area. The other use we had for heating lamps is when a plane would fly somewhere and the rampers would get too busy at the end of the night, or they get lazy and they wouldn't dump the lavatory or the water tanks, and it would get down to negative degrees something in the middle of the night up in International Falls, Minnesota, and the water tanks and lavatory blue juice would freeze solid. We'd have to fly the plane back to a maintenance base, basically put a heat lamp on the pointed at that area, the outside of the plane, to try to thaw it. But you know, so non-contact, small to large areas. The alignment and positioning is not always critical. It can be, but typically not. And you can have different ways. This graph kind of, and I know it's not the greatest, but it shows intensity over time. So pulsed is, let's see, orange here. So you do pulses of energy, pulses of light. Okay, each time you do that, it heats, right? And then you look at it as that heat either is going in or out of the part. Those are usually pretty quick, less than a second. Stepped is what color do I have stepped as? Stepped is kind of the green. You can see it kind of steps up. So you can look at it with different, you'll look at your object putting in different amounts of heat, a little bit of heat, a little bit more heat, a little bit more heat. And then looking at it as it cool down, it's kind of a controlled up and down. Modulated, so pulsed, the difference between pulsed and modulated, you can see pulsed, there's a down area. Modulated as you bring it up and down and up and then immediately start heating it again. There's no delay in the middle where you're not heating it. And then scanned heats an area and then brings it down. Now scanned, the reason it's scanned, it's not a situation where you take a light and you brighten it, and then turn it off. What I mean by scan is, you know, here's my camera, right? Is I have a heat source and I move along the surface like this, you know, where the heat source or the camera is basically following the heat source. So the area at a given point, right, it's going to get, the intensity is going to increase, and then as my heat source passes, it's going to decrease and decrease, right, at a given point. So that is what we're doing when we're scanning. Okay. Here it is a little bigger. I guess that one's easier to see. But so those are just different techniques. We can use active heating, forced air. Also, this is like a blower. Hot or cold air is directed at the surface. You can see we have a heat gun here, but this could also be something like if you have big air blower furnace, air blower heaters, you can turn those on, right? Small, large area, alignment positioning, heat guns, hair dryers, large blowers, ovens specifically, a convection oven, like what we're putting using to dry the panels on the dye penetrant bench. That's an oven that has a fan in it to circulate the air. So convection ovens, or cool air blowers, temperature decreased or observed. One of the ways that this can be done if the plane's warm, if you have like a portable air conditioning cart, is you seal the plane up fairly well, take the hose off the air conditioning cart, stick it to go to the interior of the plane, so it starts cooling the plane from the inside out, and then you can see that temperature change as it works its way. It starts to cool the skin, for instance, from the inside of the plane out. Here are direct contacts. So in this case, we're actually putting something against it. Anyone know what these are at the top here? Those are heating blankets. Where do you usually see them? What's that? Composites. Dr. Gale really, really wants a set of these. I think they started about $20,000 for a set with the controller, and they go up quickly from there. They're very, very precisely controlled heat blankets. But you can take these, what they're normally used for, you put them in your layup. They don't become part of the composite. They go above the peel ply and stuff, but they go right in the vacuum bag and they provide heat that way rather than baking the whole layup. But you can also use them to create a warm area to do an inspection on a panel. How many of you have seen one of these? Yeah, your mom pulled it out when you had an earache when you were little, made you lay on it, right? Hot water bottle, yeah. So these can be used. The big application for this kind of thing is if you need to image a fairly thick fiberglass panel, you want to get that heat right into it. You don't want to have to heat it really warm to get it. You don't want to risk delaminating it by overheating it. But you can put that heat at a given intensity over a long period of time. That's the math at the top. Obviously, the water bottle down here is going to get cold. You can even use things like bricks or blocks, like a concrete block wrapped in a towel that you've heated up. And just say, obviously on a structure where it's not going to damage it, but your other solid, a piece of metal that's been wrapped in a towel, you can set it on an area, warm it up, and use it. So there's all kinds of heat sources that can be used in a pinch. A couple others, electromagnetic heating, right? When you were doing mag particle, if you held the button down too long, your parts would get warm on the mag bench, right? That's induction or electromagnetic heating. That can be used in some applications. That's more of a production thing, looking for quality control during metallic part manufacturing. And then continuous scanning is what I was talking about. When the area is bigger than what you can do with like a single blanket or a single light, is you have a light and a camera that kind of travel with each other. And that's being automated now. That's being put into like crawlers or even like a drone, where you can do inspections with that kind of equipment. The next step we have to do is temp measurement. And so I talked earlier about the spot measurement. Most of you have used a spot detector at this point. So it allows you to measure IR radiation in one tiny little point. But it's not really useful as an analysis tool. If you're trying to analyze, it'd be really hard to go back and forth, sweep back and forth and try to remember the temperature at all these different points and compare them quickly. So that's where we get to the infrared cameras. So infrared detectors, array-style infrared detectors, were introduced in the 1960s. And you can measure that infrared energy over a given area at many thousands of points simultaneously in order to get a picture or some kind of data set that can be analyzed to perform inspection. So each pixel is given it essentially gives you an amplitude or intensity of the infrared energy being emitted from a point, and it's correlated to local surface temperature. For our use, thermography, absolute temperature, what's the actual temperature at each point, is less important than relative temperature. What do I mean by that? Yep, so the temperature of this pixel compared to this pixel, compared to this pixel, compared to this pixel. We're looking at that change. How is it, right? How is the temperature changing from point A to B to C to D to E to F to G, right? We really don't care, is it, is it 70 degrees here? Is it 68.5 degrees here? That doesn't tell us a lot. But if we know that, this is a half a degree cooler, or a degree and a half cooler than this area, that's going to tell us something. So that's what we mean. The relative temperatures are most important for what we're doing. When you start getting into more of the analysis, then having those specific temperatures can be important, but again, most of those algorithms are going to be comparing each point. The algorithms that do these, that are used for analysis, again, they're not looking at the absolute temperature, they're comparing those 180,000 temperatures that were all taken in a single image simultaneously. So there's some key performance parameters that you want to be aware of. The first is thermal sensitivity. What's the smallest temperature difference that can be reliably detected by each pixel? So our camera, the one that we're using here, the FLIR 95 or E95, has a temperature differential or sensitivity of less than 0.03 degrees Celsius. What do I mean by that? Does anyone have, this is gonna be a weird question, I promise. Is anyone wearing flip-flops or shoes they can slip off easily? Because I don't want to take a boot off right now. You guys look perfect, come on up. I need you up here. There we go, that's what I want. Oops. I promise I'm not like doing anything weird here. There we go, okay. So this is actually should be a live view. It looks like it lost. Oh, I know why it lost connection, because I unplugged it. You can hook it up by Wi-Fi, but I'm connected to the Wi-Fi in case I need to show a video. So let's see, let me plug this back in. Sorry, reconnect it. Reconnect. 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 Computer's figuring out what to do with it. Uh-oh. I really should not have unplugged it. I wasn't thinking. I was thinking it was connected by Wi-Fi, which is what I do in the classroom, but I'm also not possibly going to have to show a video there. So what do I mean by sensitivity? How close it is? Here's why I wanted somebody with shoes they could slip off. Go ahead and slip off one of your shoes. I want you to set your foot right there for just a second. 3, 2, 1, go ahead and lift your foot up. You can see, and if you look on the screen there, you can see an outline of Dugan's foot where he had it sitting there for less than 3 seconds. Yep, yeah, even where his shoe was sitting, there was heat. I'm sure mine probably, yep, see? That is from the heat from my body going through. So the difference here, if I go off to one side, go ahead and do it again real quick, since yours show up better. And I don't have this calibrated for the material, which is one thing we'll talk about in a minute, okay? So right here, the floor is about 67.3 degrees. And if I go to kind of the warmest spot, it's 70.2 and cooling down. So that's how sensitive these are. Again, this shows to the 0.1 degree, but it actually can pick up differences of 0.03 degrees Celsius, roughly equivalent to 0.03 degrees Celsius. I can't remember what that is, Fahrenheit. Okay, you're good to sit down. Thank you. Appreciate you letting me. Okay. So, we want to see a difference. We want to be able to compare pixels. This allows us to compare pixels, 0.03 degrees Celsius from one to the next. So you can see very, very tiny. This is why all we can, in some cases we can just flash a light for a fraction of a second and pick up a temperature change because of the high sensitivity of these cameras. We have another camera that a lot of you use too called the FLIR One Pro. These are ones that plug into like an iPhone or an iPad or Android. And those are sensitive to 0.07 degrees. They're not nearly as they're not as sensitive because they're not nearly as expensive. Just to give you a cost comparison, that's a $400 camera. Okay, mine, if it had the screen and everything, it'd probably be about a $600 to $800 camera. But we use those. This is like a $9,000 camera. The other thing that they have is accuracy. So accuracy is how well do they match actual. You can see here the accuracy isn't nearly as fine as the sensitivity. Right? Accuracy is basically all the pixels are going to be plus or minus 2 degrees Celsius. But again, because we're more interested in relative temperature than absolute temperature, as long as all the pixels, which it's one sensor, so all, everything in the sensors could be up to 2 degrees high, 2 degrees low, okay? But as long as they're all 2 degrees high or all 2 degrees low, which they are, then, we're looking at that differential of the sensitivity. So when the camera is properly calibrated or set up, we can measure temperatures to roughly 2 degrees Celsius or 3 degrees Celsius with our less expensive cameras. The thermal range is what kind of what temperatures can we detect? Different sensors are tuned for different temperature ranges. So the E95, the one I have here, has 3 different temperature ranges. So you can set it if you expect to image something in the -20 to 120 degrees Celsius, 0 to 650 degrees Celsius, or 300 to 1500 degrees Celsius. I have it set in, wrong button. That should bring it up. If I go in right now, the temperature range here are my temperature ranges. Actually, I'm not really in a great range. I'm in a range that was acceptable, right? We're looking at room temperatures. Usually we use the 32 to 1200 unless these are in Fahrenheit. So -4 to 248 or 32 to 1200, which is what I'm going to actually set it to because that's what we use most of the time. Or 572 to 2732 if you look at it in Fahrenheit. This camera is set in Fahrenheit right now. Yeah. The FLIR One is it only has a single sensor in it, or a single range sensor in it, -20 degrees Celsius to 400 degrees Celsius. So still more than capable for pretty much anything we're going to be doing. When you heat your panel, when I talk about putting the panel in the oven, you're really only going to heat it for a few minutes. That oven maxes out at 150 degrees, 160 degrees, right? So the array size is how many measurements are we taking simultaneously. It's the image resolution, the number of pixels. You're all familiar probably with pixel, with resolutions on your phone camera or on your digital camera, right? So, or your television if you're talking high def. So the biggest thing I want to point out though with this is the array size, the image resolution for the sensor. Okay? Not necessarily the image resolution of the screen on the device. Okay? So this camera, for instance, has a resolution of 464 by 348. How does that compare to a visible light camera that's in your cell phone? It's pretty poor. Your cell phone is thousands by thousands, right? This is 0.16 megapixels. To give you some idea, if you're used to like 12 megapixel or 14 megapixel, this is 0.16 megapixel is what that means. Okay. But again, that is the resolution of the camera that's pushing $10,000. Right. So these sensors are much more expensive than the sensors that are in a visible light camera. They're produced in much lower volume, much lower quantities, although more and more you're seeing more and more things that have infrared sensors in them. And there are inexpensive infrared sensors coming on the market. The FLIR 1 Pros we have are 160 by 120, so only 19,200 pictures. But remember, that is 161,000 or 19,000 temperatures that are all being taken simultaneously. So this camera is like having 191,472 of those heat guns all pulling the trigger at the same time. That's not the display or screen size resolution. So you may not be able to see, the screen usually is a little bit lower resolution. Your phone, when you plug in one of these FLIR 1 Pros, 19,200 pictures, your phone display's got many more pixels than what's on there. But it's still enough for do, okay? Next one is field of view. This kind of goes back, hopefully reminds you of borescopes, right? Field of view is what's the angle that we can see. Okay. And so the field of view is ultimately determined by the lens that's put in front of the actual sensor, the thermal sensor. So this FLIR 95 has a 24 degree by 18 degree lens. Okay. They refer to it in there as a 24 degree. It's because you can see there are more pixels wide than there are tall. So it's more degrees wide than it is tall, and we'll look at how pixel size relates to field of view and how one kind of can determine or skew the other. But the ratio in this case, you can see, is a 4:3 ratio, is the same as the camera resolution. So that keeps our pixels square. The FLIR 1 Pro is a wider angle. It's going to see 55 degrees wide and 43 tall. You can see this, the FLIR 1 Pro sensor is a 4:3 ratio, but the FLIR 1 Pro lens is not a 4:3. It's close, but that'll cause the pixels to be slightly skewed. So the pixels are actually slightly rectangular rather than square. It's taking a rectangular measurement area rather than a square measurement area. And where that becomes important is when we are figuring out a flaw. If we have a flaw, we're trying to find a flaw of a given size. If the manufacturer says the flaw, you can have an area of delamination, that's up to 1 inch wide. Or you can have moisture up to a certain percentage. You have to make sure that you're imaging enough pixels that you can get an accurate measurement. And the minimum number of pixels that we have to have over an area is 9 square pixels, so a 3x3 grid. And so with knowing the resolution, the array size, knowing the field of view, and then knowing what size we have to, how many pixels we have to cover an area or what given size area we're trying to find, we can figure out the distance that we have to image something at, or pretty much we can figure out what the max distance we can be away from the surface is. Because if we're too far away, those pixels are going to be spread over too big of an area and you won't be able to accurately measure to the size that you need to measure. And so next time we'll start talking about, we'll actually look at how do we calculate what the max distance is for a given expected flaw size. But just know, a lower resolution camera typically has to be closer to our test object in order, it'll result in a smaller scan area, so it's going to be slower. A higher resolution camera, you can move back, and especially with a narrow field of view, you can see this is higher resolution, narrow field of view. We can be further away and measure but still measure a larger area using the more expensive camera that has a higher resolution and the lens to go with it. There's actually this is an interchangeable lens. You can get it, this is a medium angle, you can get a wide angle or a narrow angle depending on how far away you're going to be. So we'll stop there, and next time we'll look at how to calculate these.